In this video, we're going to look at sample means and how do you make confidence intervals and how do you calculate margins of error. Now, before you get started on any problem involving margins of error or confidence interval involving sample means, you have to decide, can we use the normal distribution? Now, if you can't use the normal distribution, there are several different cases of what can happen next. But what I want to focus on now is there are two main cases when you're working confidence interval problems. The first case is when you can use the normal distribution. So let's look at that. So when I teach my classes, I have three rules about when you know what distribution to use when you're making confidence intervals. Rule 1 deals with means. So let's look at this one. And this deals with when you can use the normal distribution for a sample means problem. So rule 1, we know that sample means will be normally distributed with a standard error, standard deviation of sample means, standard error, equal the standard deviation of the population divided by the square root of your sample size when either one of these two things is true. Either A, the data we're studying is normally distributed, and we know the population standard deviation. If those two things are true, you can use the normal distribution. So an example would be you're studying IQ, which is normally distributed, or you're studying the heights of adult males, which is normally distributed, or you're studying pregnancy lengths, which is normally distributed, or SAT scores, which is normally distributed. And you know the population standard deviation of the population you're studying. So for example, you might know that heights have a population standard deviation of 3 inches. You might know that IQ has a population standard deviation of 15 in the population you're studying. You might know that SAT scores in the population you're studying have a standard deviation of 100, for example. So if those two things are true, you're studying data. The data itself is normally distributed, and you know the population standard deviation, you're good. All right, what if you're studying something that's not normally distributed? The data you're studying are not normally distributed, like income is not normally distributed. House prices are not normally distributed. Anything involving money is normally not normally distributed. And there are many other examples. So if you're studying something that's not normally distributed, but just you know the population standard deviation, so you're good there, you can compensate for the fact that you're studying something that does not have a normal distribution. The data does not. Say the individual people's incomes are not. The averages will be normally distributed. The sample means will be normally distributed as long as you have a big enough sample size. What's big enough? Well, most textbooks agree, and I agree, that a big enough sample size so that your sample means will be normally distributed is 30. 30 is usually pretty good. Now, there are situations where less than 30 is satisfactory, and there are situations where more than 30 would be required. But for the person starting out doing confidence intervals, we say 30 is a good number. And why does a large enough sample size make the sample means have an approximately normal distribution? That is due to the central limit theorem. The central limit theorem says that if with large sample sizes, averages will have a normal distribution. So this is the central limit theorem coming into play. And all the central limit theorem does is say, with large enough samples, sample means will have a normal distribution, or an approximately normal distribution. The bigger the sample size, the better, when you're studying something where the original data are not normally distributed. Okay? Now, the question comes up here, what if the data are not normally distributed and you have a sample size less than 30? You have two options, because you can't go with A and you can't go with B. You cannot use the normal distribution in this case. Your two options are, option 1, Get a bigger sample size so that you can use a normal distribution. Okay? That's normally the easiest thing. Just go get some more data to get 30 in your sample. If that's impossible, then go consult someone who has a PhD in statistics. I'm serious. Do it. If you want your answers, if you want your confidence intervals to be accurate, go consult someone who really knows statistics. There are some ways around this, but you cannot use a normal distribution and hope that your confidence intervals will be accurate. Now, there's a second question that you might ask here. For both A and B, and this is kind of hidden in here a little bit, what if you don't know the population standard deviation? Because both of these, A and B, say you can't make a confidence interval using the normal distribution if you don't know the population standard deviation. What do you do then? Well, so rule one, if A and B are true, A or B, not A and B, but either A or B are true, then you use the normal distribution, which we call a Z, right? A Z-score. You use a normal distribution table. So what if this second thing is a problem? We don't know the population standard deviation, and this is real life because most of the time if you don't know the population mean, you probably won't know the population standard deviation either. So what do? Well, here's rule 3. Excuse me. So my rule 2 is for population proportions, and we'll do some population proportions problems in the next video. Here we want to focus on means. So my rule 3 is for just this case. What if you don't know the population standard deviation? Well, rule 3, all it is it's rule 1, where we have removed this part right here where we say we know the population standard deviation, okay? So the only difference is we don't know the population standard deviation. What do? Well, what you have to do is you have to estimate the population standard deviation with S, the sample standard deviation. So if you have to calculate the standard deviation you're using from the sample you collected, and you're estimating the population standard deviation with the sample standard deviation, notice that everything else in A and B is identical to rule 1, except we have to estimate the population standard deviation. What do you do then? Well, instead of using a normal distribution, Z's, what we use is what we call a T-distribution. T-distribution. And we use a T-distribution. Another piece of jargon or a definition you need to know is degrees of freedom. Degrees of freedom. So n-1 degrees of freedom if you don't know the population standard deviation. So here's the lesson. Here is the overall lesson here. If you could use the normal distribution, except for one fact, you don't know the population standard deviation, use the T. Use the T distribution. So the T distribution was invented for and is used in cases where you don't know the population standard deviation and you have to estimate the population standard deviation from your sample with a sample standard deviation. End of story. That's why the T-distribution exists. Now, it is actually used for some other things, but for confidence intervals, that's what you want to memorize. Use the T-distribution when we're using a sample standard deviation. Use the T-distribution when we don't know the population standard deviation. So let's talk a little bit more about this T-distribution. But before we do, let's look at a situation where we would use the normal distribution and see what's different. So suppose we could use the normal distribution and we wanted to make a 95% confidence interval. Then we'd say 0.95 is our confidence coefficient, and that leaves us with an alpha of 0.05. What that means in a graph is we're going to want 95%, 0.9500 in the middle. That 0.05, that alpha, is kind of our unconfident coefficient. That's how uncertain we are that our population mean will be in the confidence interval we're going to create here. We split that alpha in two, and alpha over 2 goes in each tail. And again, why do we care about that? Because that's what you need to hunt for in the probability section of the z-table. And when you find what z-score leaves 95% in the middle, you're going to get z equals minus 1.96 over here, and z equals positive 1.96 over here. And then in order to make your confidence interval, you would take your sample mean plus and minus your your margin of error. Your margin of error, E, is your margin of error. And what is E? Well, E, the margin of error, is calculated this way. It's your Z that you found here, 1.96, times your standard error, standard deviation of sample means. And what's the standard error? Well, your standard deviation for sample means is calculated this way. It's your standard deviation of your data divided by the square root of n. And now that's everything you need to know to calculate a confidence interval. And we'll calculate some practice ones. Actually, instead of talking about practice ones, let's do one now, and then we'll get back to this t-distribution idea. So what if we had this following problem? And the problem says, so here's our example. Let me do that in a different color so that we can see that it's something different. So example. Suppose that we were studying IQ, and we go out and we take a sample of 100 people trying to figure out what is the population IQ for a particular group of people. Maybe these people live in a certain country, right? And we know that in general, say in the United States, we define the population IQ to be equal to 100. But suppose we go out into a rural area of the United States and we don't know what the population mean IQ is for people in this small town. So we don't know the population mean. That's what we're trying to figure out. So what do? We take a sample of 100 people and we give them an IQ test, and we find that the sample mean equals, say, 98.2. What do we do if we need to make a confidence interval? Well, it depends on whether we know the population standard deviation or not. Let's suppose someone tells us that they're sure that they know the population standard deviation of the people in this rural area is the same as the standard deviation overall, which is 15 for IQ. Then we can make a 95% confidence interval, and we would just do this. It's the sample mean, 98.2, plus and minus. We're going to add and subtract something from this sample mean to make an interval. And the z-score, 1.96. And it doesn't matter if we use the minus 1.96 or the plus, because we're adding and subtracting this. So z times the standard error. Well, what is the standard error going to be? Well, we have to calculate that. Let's do that over here. It's the 15, the population standard deviation, right? So we're using this formula, divided by the square root of n, square root of 100. And so that standard error is going to be 1.5. So we'd say 1.5 here, okay? Now we're making a 95% confidence interval. So we want to say that we are 95% sure, so we're 95% confident or sure, that the population mean IQ of people in this rural area is somewhere in this range, 98.2 plus or minus 1.96 times 1.5, 2.94. Okay, so that 2.94 is what we call the margin of error. We're 95% sure that we are within 2.94 of whatever the truth is with our sample mean. And so we're going to be 95% sure the population mean is somewhere in this range, 98.2 plus or minus approximately 3, within approximately 3, a little bit less. Now, how does this change if we don't know that population standard deviation? That is the critical thing that allows us to use the 1.96 because we're allowed to use the normal distribution. Suppose we can't use the normal distribution. What do we do then? Well, as long as we can use rule 3 here, we can use the t-distribution. And I'm going to introduce you to that t-distribution table. So the data we're studying are normally distributed. Yeah, IQ is normally distributed. But even if it wasn't, we have a sample size bigger than 30 here, because I said we took 100 IQ. So either way, we can use the t-distribution. But in this case, somebody says, whoops, we don't know what the population standard deviation is of IQ in this region. Sure, for the United States it's 15, the population standard deviation, but we really don't know what it is here. So what we have to do instead is say, let's take our data, our 100 IQs, we put it into Excel, and we say, Excel, tell us, what is the standard deviation of our sample? S, right? It calculates a sample standard deviation. Now, how does it do that? Well, I mean, if we had to do it by hand, here's the formula for the sample variance. You take each IQ, you subtract the sample mean from it, and you square it, and then you divide it, you add all those things up, and then you divide it by n minus 1. That's the sample variance. And then you take the square root of that to get the sample standard deviation, right? So suppose that when we do this, our sample variance is, let's say, 221, right? So maybe it's 221. So let's suppose it's 221.3. Just for the sake of argument. That's what Excel tells us. And then we take the square root of that. And we get that our sample standard deviation, S, is 14.88. I'll round it off there. 14.88. Just the square root. Now, because we don't know the population standard deviation, and we're using a sample standard deviation. In other words, we're taking our data we collected to calculate an estimate of what the real standard deviation we should be using is. We have to use something called the t-distribution with n minus 1 degrees of freedom. So a t-distribution with n minus 1 degrees of freedom. Now this is a mysterious term. What in the world does that mean? Well, in general, what degrees of freedom really means, let me rewrite that because my handwriting is really bad today. Okay, what degrees of freedom generally means, it's actually a very technical mathematical term, but what it means in this case is, how much data do we have in compared to, or what we have to subtract from how much data we have, which is 100, right? We have 100 IQs. Anytime you calculate something from that data, before you calculate the standard deviation, you have to subtract that off. Now, what in the world am I talking about here? Well, what I'm talking about here is, how did we calculate the standard deviation? Well, we had to calculate the variance, sample variance. But before we had to calculate the sample variance, we had to calculate the sample mean to do that. So that uses up some of the data in a way. And again, this is a very mysterious concept. I'm not going to explain the deep mathematical meaning behind it. But why we're using n minus 1 here, it's actually the same reason why we're using n minus 1 there in that formula instead of n. It's because when you calculate a sample mean and then you calculate a sample variance from it, it's like you used up part of the information. So n minus 1 degrees of freedom. Okay, still, what does this mean, you're asking me? Okay. What this means is when we go to calculate our confidence interval, we're going to have to calculate it this way. Instead of our margin of error being z times a standard error, our margin of error is going to be equal to a t, which is related. The t-distribution, sometimes it's called student's t-distribution. I'll write that over here, student t-distribution. Because it was invented by a guy, let me just give you 10 seconds of his history here, invented by a guy named William Gossett. And William Gossett, G-O-S-S-E-T, I think it's just one T, William Gossett, he invented the student's t-distribution while he was the head brewmaster for Guinness Brewing Company. Yes, believe it or not. But his employers at Guinness Brewing Company, William Gossett was also a brilliant mathematician and statistician. They would not let him publish his scientific papers using his own name, William Gossett. So he chose a pen name, and he called himself Student. And so when he was doing research, inventing this t-distribution we're getting ready to look at, he published it under simply the name Student. And so we call it Student's t-distribution. But it was really this guy named William Gossett who was a brewer. He was a master brewer for Guinness Beer Company. So anyway, when we calculate this margin of error, instead of a z times a standard error, it's going to be a t times a standard error. Okay? But the t and the z are serving the same function. The z told us how many standard errors we need to go above and below the mean to get our confidence interval. The t is going to be doing the same thing, and it's going to be a similarly sized number. It's just going to be a little bit different. Now, one other change that we make here, since this notation here, standard deviation of sample means, this has a sigma in it. When we're using a t, we don't use that lowercase sigma. Instead, we use s, x bar. Now, why don't we write sigma? Well, because we don't know sigma. We don't know the population standard deviation. So instead, since we're using an s, we write s there. But how do you calculate this standard error with an s? It's exactly the same way you do if you don't have the sigma. You take your standard deviation, your estimate, and you divide it by the square root of n. Okay? So in this case, what would our standard error be? It would be 14.88, because that's our estimate of the standard deviation, divided by the square root of n. Well, we still have 100 IQs that we collected from people. So it would be equal to 1.488. Right? So that's what's going to go right here, 1.488. Now we need to figure out what t are we going to use here instead of a z, because we can't use the normal distribution. We have to use this thing called a t with n minus 1 degrees of freedom. Okay, well, it turns out before we go to the t table, there are only two things you need to know to figure out what t to use. So what t to use is going to be based on two things. N minus 1, that's the degrees of freedom. And in this case, since we have a sample of 100, that's going to be n minus 1. 100 minus 1, 99. And the other thing you need to know to figure out what t you should use is alpha over 2. We need to know that, just like we did when we were looking up what z-score to use. And remember that alpha over 2, if we want to be 95% sure, alpha is 0.05. Alpha over 2 is 0.025. So you need to know that alpha over 2, and in this case that is 0.025. Now, armed with that information, n minus 1 is 99, degrees of freedom. Alpha over 2 is 0.025. Let's go look at a t-table now to see what t we're going to plug into this formula to get our margin of error. All right, here's a t-distribution, and you can go to www.berkeyacademy.com and you can click on Files on the left side and you can download one of these. And on the front side of what you download will be a normal distribution here. And on the back side will be this t-distribution. So when you're looking up a t, I said you need to know two things. N minus 1 degrees of freedom, that's right here. So these rows are different degrees of freedom. 1, 2, 3, 4, 5, 6, 7, 8, 9. And over here I pick up with 51 to 60 to 70. So if we have 99 degrees of freedom, that means that we're looking at this row right here. This row. So let me highlight that row. Now, what column we look in order to get a t value. So these are the t values here that you put into formulas like margin of error. The t value you get by looking at degrees of freedom, that's the row, and the column is the area in the upper tail. That's that alpha over 2, okay? So what we want to do is look at the column here for alpha over 2. So let me highlight that column. And so if we look at the intersection of the column alpha over 2 and the row 99 degrees of freedom, that tells us that the t we need to use in this problem is 1.9842. 1.9842. So let's go back and look at our problem we're working on and fill it in and calculate our our margin of error and our confidence interval. But one thing to notice before we do that is, how does this 1.9842 compare to the z that we were using? Well, we were using a z of 1.96, and here's how to understand the t-table. What the t-table is doing is it's always going to give you a t that is a little bit bigger than the z. And the reason why it's given us a bigger value is because we're uncertain about something. We're uncertain about what the right standard deviation is. We don't know the real standard deviation. And so this t-table gives us a bigger number to multiply times our standard error that's going to make our confidence interval a little wider. And it just shows that uncertainty we have about what the real standard deviation is. It makes our confidence interval wider to take into account that uncertainty, okay? And one other thing to notice here, before we go back, since we're on the table, is what happens as the degrees of freedom go down. 1.9842, as they go up, here is, what if we had 1 billion degrees of freedom? Look what that turns into, 1.96, the same as the z. But as you get lower degrees of freedom, this 1.9842 gets a little bigger, 1.9876, and here it's 2. And if we look over in this column where we have really, really small degrees of freedom over here, we have the numbers going to 2 and eventually up to 3, 4, and 13. That's if we only had a sample size of 2 and we had 1 degree of freedom, 2 minus 1. We would have to make a really wide confidence interval. Why? Well, the smaller your sample size, the worse your estimate of the standard deviation is. Okay, so here we are back, and we need to use that t that we looked up here, and that t we looked up with 99 degrees of freedom and an alpha over 2 of 0.025 was 1.9842. And so again, when you look up a t on the t table, make sure that it's a number that's a little bit bigger than the z that you would use in that situation if you were using the normal table. It's always going to be a little bigger. So let's finish our confidence interval. We plug that 1.9842 in here, 1.9842 times our standard error of 1.488, and then we take our mean. Suppose we had the same sample mean, 98.2. To get our confidence interval, we just take the margin of error, 1.9842, so 1.9842 times 1.488 gives us a margin of error of 2.95. And then we would make our confidence interval by taking the sample mean plus and minus 2.95. And since our sample mean was 98.2, let's just plug that in there. So we would be, just like when we use the z, the interpretation is no different. We would be 95% sure that the population mean, IQ, for people who live in this region, is somewhere in the range 98.2 plus or minus 2.95. Okay? And that's the only difference between these two problems is, in the first problem, we said we knew the population standard deviation was 15. And so that allowed us to use a z-score of 1.96. In the second problem, because we don't know the population standard deviation and we have to calculate an estimate, we take our data, we calculate a sample standard deviation. That's what forces us to use this t-distribution. And that is why the t-distribution was invented by this guy, William Gossett. He was a brewer. And what he found was, when he actually used this mathematics, he used confidence intervals when he was making beer. One of the applications was he wanted to be able to count up how many yeast cells were in the beer when he was brewing it. Because when you make beer, you need water, hops, malt, and yeast. And so when he would put yeast in, he would want to know how much yeast he was putting in to make the beer. So he would look at different samples, tiny little samples of the liquid he was pouring in under a microscope, and he would sample different droplets to see how much yeast were in there. But he didn't know the standard deviation between the droplets when he was counting. Okay, so that's why he said, you know, if I want to get an accurate confidence interval, I'm going to have to invent something besides using the normal distribution. And people later called it student's t. And that's where we get this table from. So this is how you work sample mean problems. Now, this video is getting plenty long. I'm going to come back with 2 more example problems in the next video and see how we decide from a textbook kind of problem, how do we decide what to do and how do we calculate these confidence intervals.